So the first talk opening the first session will be Eran Palti, who we're very happy to have tell us about the emergence of kinetic terms in string theory. So please go ahead.
Okay. Hi, everybody. So let me first of all thank the organizers for all the hard work in organizing this spectacular workshop and for the opportunity to speak. It's really an amazing setting. Okay, so the title of my talk is Emergence of Kinetic Terms in String Theory, and it's based on these two papers with Jawad Hattab, who is my PhD student. So let me begin with some motivation. Central Swampland constraints relate kinetic terms to towers of states. For example, the weak gravity conjecture relates the gauge coupling in front of the kinetic term for the gauge field with the mass scale of a tower of states. The distance conjecture can also be thought of something similar. You look at the kinetic terms for scalar fields, and this defines for you a field space metric. And then you can use this metric to define a distance. And then we say that at large distances, you get a tower of states whose mass scale is set by the distance. The emergence proposal is something that tries to understand a little bit what could be the underlying physics behind this kind of behavior. And it proposes that these Swampland conjectures are manifestations of the fact that these kinetic terms of field are emergent in string theory or quantum gravity. It is an idea that's been around for a few years now, and a lot of people have worked on this one way or another. I won't go into this too much. So let me give a toy model to have something in mind for what could be a relation between emergence and towers of states. So this toy model is this CPN model, which is a very old model. And here we have n scalars, Zi, and this is the action for the Zi's, and it has a covariant kinetic term, but the gauge field is not independent, it's just a collective vector mode of the Zi's themselves. So, and there's no kinetic term for this gauge field, so this is the whole theory. So it's just a theory of n scalar fields. This is somehow the UV theory, and then if you float it infrared, the theory becomes strongly coupled, and these scalar fields are strongly interacting, and you get a gap. The theory gets a gap, except it's not quite a full gap, because this combination of fields transforms under a U1 gauge symmetry of the theory, just like a gauge field. So it's a theory with a U1 gauge symmetry, but no propagating gauge field. And so it cannot get a mass, and therefore the infrared spectrum is just the polarization, two polarizations of a gauge field. So it's just a massless vector. And by the time you float it infrared, you also generate a kinetic term for this field. So the infrared theory just looks like a Maxwell theory. This is an example of an emergent gauge field. There's no propagating gauge field in the UV, but there is one in infrared. The better way to think of it is in terms of a duality. These two theories are infrared dual. So Maxwell theory is infrared dual to this theory. Now, the interesting thing to note is that the gauge coupling for this emergent gauge field looks like it's just been generated by one loop integrating out the massive states, except normally you would have a tree-level contribution plus the one-loop contribution. Because this gauge field is emergent, the whole thing is just a one-loop contribution. So that's the smoking gun signature of an emergent gauge field. It just means that the tree-level kinetic term comes from one loop integrating out the states that are dual, infrared dual to the gauge field itself. This is the kind of thing we're going to be looking for. So in string theory, the claim is that something like this holds. It's realized a little bit differently. This is some infrared field, like a gauge field or a scalar field. The claim is that it's infrared dual to some tower of states. And this duality, this relation, is what's responsible for this kind of relation between the mass of this tower of states and the gauge coupling. Here, this is the definition of the gauge field. There is a gauge symmetry. There's a gauge symmetry. It's not dynamical, no.
I'm saying that one usual definition of CPN sigma is n fields to the gauge to one field.
No, there is a gauge symmetry, but no propagating gauge field associated to it.
So it's not the usual linear gauge case.
No, it's something different. Yeah. Okay, and so now typically this will not be the lightest Taylor states. The lightest Taylor states will typically be a KK modes or string oscillator modes, but there'll be one of the higher towers. And the job of these lower towers in some sense in this proposal is to make sure that you run to strong coupling by the time you hit this tower, because this duality is a strong weak coupling duality, so you have to hit strong coupling by the time you reach this description. So that's the picture that we propose in string theory. And how are we going to test this now? So remember I told you the smoking gun signature is that the tree-level kinetic terms come from integrating out the tower of states, the states in the UV. And what we're going to do is we're going to do this integrating out in a background field formalism. Okay, and the simplest example of this is the Euler-Heisenberg Lagrangian. Euler-Heisenberg Lagrangian is just QED after you've integrated out the electron in a background field. And when you do that, this is what the Lagrangian looks like. There is a tree-level kinetic term coming from the tree-level kinetic term of QED. And then there is the contribution from diagrams like this, where you've integrated out the electron at one loop. And this integration out can be done by a Schwinger proper time integral. And you just get a bunch of terms, an infinite number of terms in F, the field strength. Okay, so this would be the one loop contribution. And if this was an emergent gauge field rather than QED, this term would be absent. And the whole of the effective theory, the whole of the effective Lagrangian for the gauge field strength would just come from this one loop contribution. Okay, that's the analog thing to be showed it for the CPN. This is what you would see in a background field calculation if the gauge field was emergent. This is what we're going to try and test in string theory. The setting we're going to consider is type 2A string theory and Calabi-Yau manifolds. And in this case, you have vector multiplets. We'll consider just one vector multiplet, which has this scalar component T. And the vector multiplet sector is controlled by a prepotential. It's called a genus 0 prepotential. And this is like, if you like, the gauge coupling, the analog of the gauge coupling in supersymmetric theory. And T is the parameter that you can vary. And the prepotential looks like it has a polynomial so-called tree-level piece. In particular, the T-cubed piece is the dominant one. That's what you might call the dominant classical gauge coupling, control of the gauge coupling. And then it has these non-perturbative exponential contributions as well. It turns out this controls the two-derivative effective theory. Also, there are also higher derivative terms. Just like in the Euler-Heisenberg Lagrangian, you get an infinite number of Fs. Similar thing here, W would be the graviphoton background field that you did a calculation in, and you get higher derivative terms. They are controlled by higher genus prepotentials. Okay, now we're going to try and do an integrating out calculation and compare that to the prepotential and the effective theory, and this was done in this seminal work of Kupakuma and Waffer. And what they showed was the following. You can take the non-perturbative pieces, that's the exponential parts of the prepotential, of the various genus prepotentials, and sum them all up into an all-genus prepotential. And then they showed that this comes from exactly a Schwinger one-loop calculation, where you integrate out UV states. In this case, they are D2, D0 branes. And because, unlike QED, where there's just one electron, here there are many such states, so you have to sum over all of them. So in this case, they are parameterized by the wrapping number of the D2, the D0 charge, and the genus of the wrapped curve. And then what they said is that this thing, that's basically the Lagrangian, the effective Lagrangian for the graviphoton field strength W after you've integrated out all these states. This is the complete analog to the Euler-Heisenberg Lagrangian. And they said that this is equal to the non-perturbative part of the prepotential. Now, I write here infrared on top of this effective Lagrangian, not because it's an infrared effective Lagrangian, though it is, because this Schwinger proper time integral has a cutoff, epsilon, which is a UV cutoff. And therefore, when you've integrated out the states, you've only integrated out the IR part of the states. So we have not integrated out the UV modes of these states. That's a natural cutoff to put on, and we typically have to do that. But that's because we've cut off the UV contribution, I call this the IR Lagrangian. Okay, now what does the emergence proposal say? The emergence proposal says the full prepotential should arise from integrating out the non-perturbative dual tower states. That's precisely the smoking gun signature we're after, a background field calculation where we reproduce the tree-level pieces from integrating out the states. Now, how can that work here? Well, this is what we propose. This is what was shown by Kupakuma and Waffer. And now we say if you remove this UV cutoff, you set epsilon to 0, that means you integrate all the way to the full UV, you will get new contributions to the effective Lagrangian coming from the UV modes, and then you will reproduce the full p-potential, including the tree-level terms, including the cubic pieces and polynomial pieces. That's the proposal. Now, we should say this was first attempted, and this is what inspired us in this group of people, and we do things a little bit differently, but certainly they should get the credit, I think, for revisiting this idea. Now, the question is, how do you UV complete this integral? When we do Schrödinger integrals, we always put a UV cutoff. How do you integrate to the infinite UV? There's problems if you do that. First of all, the integral is just divergent. You get divergences from the poles at s equals 0, but you also get further divergences because you have to sum over infinite number of states, and if they're not suppressed by an exponential, you just get a divergent sum. So this is highly divergent, naively highly divergent if you set epsilon to 0. And secondly, we should not even be allowed to do it because we're integrating out wrapped branes, and so we're treating them like particles, and therefore we should be looking at distances much larger than the size of the branes. Whilst if we integrate to the full UV, we'd be probing distances much smaller than the branes. We cannot treat them like particles anymore. We should somehow quantize them and integrate out their fundamental degrees of freedom. That's what we would have to do. What we're going to propose is a way to actually regulate this integral and do the full UV integral. We're going to actually show how to do it 2 different ways, and that reproduces the full pre-potential. That's the rest of the talk. So we're going to look at an example, the resolved conical. That's a non-compact setting with a single 2-cycle. And the genus 0 pre-potential for this setting is given by this formula here. There is the tree-level pieces here, especially the cubic term, but also the other polynomial pieces. And then there's these exponential terms as well. And as I told you, these exponential terms come from integrating out the UV degree, the tau L states with a UV cutoff epsilon. The way to see that is you just do, in this case, it's just a single D2, so you have to sum over the D0s. You can then Poisson resum it like this, and you turn this sum of Schrödinger integrals into a sum over integers, and that precisely reproduces this logarithm here. Now, if you were to try and UV complete this, you would have to remove this epsilon cutoff, and you put a 0 here, and then you see what you do is after this Poisson summation, you pick up the delta function at s equals 0, and you just get something that's very, very divergent. So we have to deal with this divergence in some way. And there is a way that we propose how to deal with it. It goes like this. Take this sum over the D0 branes of the sum of the Schrödinger integrals, and you do a Poisson resummation, and you turn it into a sum over Schrödinger integrals like this, with delta functions which localize the Schrödinger proper time over the integers. And you can rewrite this whole sum of Schrödinger integrals as one complex integral. So you can think of it as analytically continuing the Schrödinger proper time, and then taking a contour which includes all the positive integers. So this is just an equality, it's just a way to rewrite this whole sum over all the integrals as one complex integral like this. Okay? So this is, you can think of it as analytically continuing the Schrödinger proper time. And S, the real axis, is the Schrödinger time, and then S equals 0 is the UV contribution that we were not including. That's the divergent contribution we had in the naive integral. But now, after we've done this analytic continuation, we can actually take a contour over the origin. We can now include this UV contribution, and when you do that, you get something finite. In fact, you get precisely the tree-level piece of the pre-potential. And this, therefore, we claim is evidence that the tree-level pre-potential does come from integrating out the states, but you have to include the UV contribution of those states. So that's how we interpret this. And in this sense, we would say the field is emergent. It's emergent from the D2, D0 branes, and you just have to do the full integral. Now, can we see this integrating out even more directly? I said we'll show it 2 ways. This is the second way you can see this integrating out. We don't have to do this analytic continuation. Can we see it from standard integrating out? We claim the answer is yes. But as I told you, because we're doing integrating out to the full UV, we can't treat the branes as particles anymore, but rather we have to resolve them into their constituents, and then we have to integrate out the constituent. And there is a way to do that for certain type 2A settings. It's developed in this beautiful paper. You have to extend the, instead of switch the expansion in terms of G string for an expansion in 1 over G string, or this H bar. And if you do that in that settings, it turns out that certain type 2A backgrounds can be described in terms of a Fermi gas in this picture with this coupling constant instead. And that Fermi gas of a fermion will essentially resolve this branes into the constituents, and then we'll just have to integrate out this fermion gas. So here's a prototypical example. Consider a blown-up conifold, which is a non-compact cone over a base, which is P1 times P1. And it's known, what is known about this theory is that the exact all-genus fully non-perturbative prepotential can be matched onto the grand canonical potential of a free Fermi gas of a two-dimensional fermion in an external potential. So this is what they showed. This is the full all-genus prepotential. You can match it onto the grand canonical potential. Grand canonical potential is something that's associated with a one-particle Hamiltonian. In this case, the particle is a fermion, a two-dimensional fermion. GS and H bar are related like I wrote before in the previous slide, and you have to relate now the chemical potential to the scalar modulus, and this is the exact relation. And under this relation, this is an exact fully non-perturbative relation. Most importantly for us, they're mostly interested in the exponential terms, but we're interested in the polynomial terms, and this F includes the polynomial terms, including the cubic term. Okay? Now, how should we understand this relation between the grand canonical potential of a two-dimensional fermion and the prepotential? And our proposal is that this, in fact, should be understood as nothing but an integrating out calculation. You're just doing an integrating out of this UV degrees of freedom, and just like in Guber-Kummer-Waffer. So to see why this should be the case, you can look at a simple toy model of a two-dimensional fermions on S1 times R. That's where this Fermi gas model lives on. And you just put such fermion every point in space-time, in four-dimensional space-time. And this is the theory that you take for this two-dimensional fermion. You couple it to a gauge field that you give a background to, and that's we call mu. That's how you introduce a chemical potential in a quantum field theory. It's just a background for a gauge field. So that's going to be the chemical potential. And now we just integrate out this fermion. If you do that, this is kind of standard calculation, you can do it. You find an effective theory for this background gauge field, so for this chemical potential. And the effective theory that you find is exactly equal to the grand canonical potential of the associated to the one particle Hamiltonian of this two-dimensional fermion. So this J that appeared before is actually nothing but the effective theory after you've integrated out the fermion. Just the same thing we've been encountering so far. This is a toy model, but we believe that this is showing that all this is doing is just integrating out the UV physics. How would this be realized in the actual type 2 setting? Well, the way to understand it is like this. In the Guber-Kummer-Waffer calculation, you send a string coupling to infinity, and you send the graviphoton background to 0, so that you still have a good genus expansion in the expansion parameter, which is G string times W. Whilst here in the Fermi gas approach, you keep the graviphoton background constant, you set it to 1, and so now the expansion parameter is going to infinity. You don't have a good genus expansion, but you do have an expansion in 1 over GS, which is this H bar expansion. So this is nothing but the same calculation, except in the background of a graviphoton, which is 1 rather than 0. What we showed is that what we see is that this prepotential we told you is given by this grand canonical potential, but then I said that this is nothing but the effective action that you get when you integrate out the fermion. And so we see this relation again, that the full prepotential is just what you get when you integrate out the UV degrees of freedom. And so we say that this is a second, more microscopic way to see the same thing. If you integrate out the UV, you generate the full prepotential. So this was so far done for non-compact settings. These are non-compact cones over some base, two-dimensional base. But if you wanted to make contact with a swampland, we have to do it in a setting which is compact, where gravity is dynamical. Can this work for compact settings? Our argument is that the answer is yes. So here's a simple example. You can consider elliptic vibration over a toric base, a reflexive toric base. And this T would now be the size of this base. And this is a toric base, so it's specified by some toric vectors, nu a's. And then what we want to do is write down some Fermi gas Hamiltonian, such that when you integrate it out, you will generate the tree-level term in the prepotential. And the Hamiltonian associated to this system is just given in this form here. And this is known in topological strings as a spectral curve in the case where it's a non-compact setting, but you can also do it for a compact setting with an elliptic vibration. And then if you integrate out the fermion associated to this Hamiltonian, you will get something that's a function of the chemical potential. And then you need a map between the chemical potential and this modulus T, and this is how the map is determined. And this will indeed reproduce for you the cubic term in the pre-potential from the fermion with this Hamiltonian. Now, we don't know, this will not reproduce the exponential terms, it only reproduces the cubic term because that's the leading term at large chemical potential and at large energies. So this Hamiltonian should be thought of as the Hamiltonian as capturing the high energy modes of this system. We do not know how to reproduce the full exponential terms, but we're just interested in this cubic term for now, and that's why things are much simpler than when people considered it in the past, because they were mostly interested in the exponential terms, which are much harder. Now, we propose something even more general. We propose that for any compact Calabi-Yau, let's consider one parameter Calabi-Yau, we should identify the period of this Calabi-Yau with the grand canonical potential of the UV system, be that a free Fermi gas or not. Okay? It could be something else. You calculate the grand canonical potential. The claim is that the classical grand canonical potential should be identified with a period. So here's an example. You take this Calabi-Yau. It has one complex structure modulus, if you like, at the mirror, or one Cayley modulus at the mirror, and you identify this thing with the chemical potential. And then you identify the classical grand canonical potential with the period. And the period has a Mellin-Barnes integral representation, which is just like the Schwinger integrals we discussed before, and can be understood as integrating out the UV. So what we propose is that if you integrate out the UV degrees of freedom, you generate an effective action for the chemical potential mu, just like you see here. And then you need to relate this mu to the Kähler modulus through a map. And this is the map that you can determine works. It's only the leading order piece. It's infinite mu. It's the map between infinite volume and infinite mu. We don't know how to reproduce the lower order ones, but this is all you need to reproduce the cubic piece. So that we claim is true for any Calabi-Yau. So to summarize, we argue that tree-level kinetic terms in type 2A string theory determined by the cubic prepotential should be thought of as emergent from integrating out non-perturbative states. We've done it in two ways. We propose how to UV complete the Schwinger integrals by an analytic continuation. And we also gave a microscopic understanding through a strong coupling Fermi gas picture. And the prepotential is determined by the effective action after integrating out, in this case, a two-dimensional fermion. Now, it's important that the integrating out you do is for a second quantized two-dimensional fermion. This is actually, in the full string theory setting, would be a very non-trivial calculation to do because the geometric dual of this fermion model, the number of fermions is equal to the number of branes in the geometric dual. So you're doing an integrating out without a fixed number of branes. So that's some kind of string field theory calculation, but for non-perturbative states. So in the full thing, this would have to be some kind of highly non-perturbative setting, but you can just do it in the toy model, integrate out a fermion, a second quantized fermion, and you get indeed the grand canonical potential. And we began playing with these ideas in compact cases with dynamical gravity. Thank you.